Thanks, everybody, for coming in to Painting with Light. I'm really excited to get to talk about this because it's a passion project of mine that's derailed my life for the last year and a half or so. And it starts with my laptop freezing. All right, 1 second. Hey guys, are the displays supposed to be updating? Because I don't see any change. Like I'm going through slides and it's changing on my laptop, but it's not actually moving over here. Anything? I'll try plugging it back in, I guess. You would expect that to go away, right? Once I've unplugged my laptop. So I think the display is frozen. There we go. All right. Well, this starts in the 1940s with the Manhattan Project, which was a group of scientists working in secret for America to build the world's first nuclear weapon, the atom bomb. And while the results of that research were horrific, the technological breakthrough can't be denied. It was an incredible project, and they had many physical, computational, and technical obstacles to overcome. And one of the biggest was called the neutron diffusion problem. And the neutron diffusion problem comes down to the fact that neutrons are tiny particles that behave chaotically, and their motion is unpredictable. You know, the way that a neutron takes a path around a space is based on subatomic interactions, and you just simply can't model them. There are too many variables, too many potential inputs leading to different results to create a standard model that a human could solve. Fortunately, around this time, the ENIAC computer was being used by the US government, and so what they started doing was using statistical methods to say, all right, well, let's just say that we have one neutron and it starts at this random position with this random initial state. Let's see how it would move around inside of the bomb. And then take this other neutron and see how it would move around. And then just repeat that thousands of times and plot all the movements of all the neutrons that we calculate out and then statistically sample them to see where a neutron is most likely to be or least likely to be. So we couldn't predict where neutrons would move, but we could predict where they were most likely to be. I'm just going to have to keep on, plugging this in and resetting it, apparently. How's that? The screen still seems frozen. There we go. Okay, so because this technique was based on sampling starting with random numbers, the scientists named it Monte Carlo integration, after the Monte Carlo casino. And that name has stuck to this day. And then 40 years later, a computer scientist named James Kajiya was working on building more realistic computer graphics. And Kajiya found the Monte Carlo techniques, and he was like, well, neutrons and photons both behave in these chaotic patterns, and I'm interested in finding the paths that light takes, that photons take. And so he applied Monte Carlo not to building a weapon, but to actually simulating light in an environment. And he published a paper called simply the rendering equation that demonstrated that if you could process this integral, you could create an image that was indistinguishable from a photograph because it statistically simulated the actual movement of light. And at the time, this was mostly an academic exercise. You can see here, this is actually a rendering taken from his original paper. It's low resolution. It's a single sphere on a single plane with pretty rudimentary materials by today's standards. And that was because we didn't have the computing resources at the time to fully take this integral. Path tracing was the algorithm that was the way he named this algorithm, but he didn't have the computational resources to actually trace very many paths. And that was because at the time, a gigaflop cost $44 million. right? So this was academic in the 80s. And then, a decade later, Toy Story came out. Who here remembers Toy Story? I mean, this movie changed my life, right? I wanted to be a 3D animator as soon as I saw Toy Story. It was amazing. And Steve Jobs, who was running Pixar at the time, famously said that there are more PhDs working on this film than on any other in movie history. Right? And that's because Toy Story was the first feature-length film to be created entirely inside of a computer. There were no real cameras or sets or props involved. It was all a simulation. And actually, nobody knew at the time whether or not that was going to be successful, since it was the first of its kind. It cost $30 million to make, and it was a partnership between Pixar and Disney. And Jobs said that, if it makes $100 million, then both Disney and us will be happy with that. If it makes $200 million, that would be amazing. And Toy Story ended up making $364 million, proving that being able to generate realistic images was a valuable asset to have. At the time, a gigaflop cost $46,000, and because of that, Toy Story didn't fully use the rendering equation. They just didn't have the computation available at the time to make that feasible. So instead, they approximated some of it and used different techniques that required things called bounce lights, where artists would manually place lights around a scene where they kind of thought paths might go, but it was really a sort of a melding of man and machine that led to Toy Story looking as good as it did, because the rendering system wasn't great at the time. One more decade passes, and Monster House came out. And Monster House wasn't nearly as big of a commercial success as Toy Story. But what Monster House did was it proved that you could use the rendering equation throughout a feature-length film and make beautiful photorealistic images, and that the technology was there. And Steven Spielberg released this, and even though many of the audience didn't see it, it changed the industry, because it basically said, we can do this now. And from that moment forward, every major studio started looking forward towards path tracing and Monte Carlo integration. And the reason it was feasible is because by 2006, a gigaflop only cost $57, down from $46 million back when Kajiya's paper was first published. And then, one more decade passes, and Disney has secretly been working on their largest research and development effort to date, called Hyperion. It took 3 years to develop, and it was their in-house path tracing render. And they built it just so that they could render their vision for the movie Big Hero 6, which came out in 2014. And it solved many of the problems that Monster House had run into, the graininess and the low light, And to do that, it took an incredible amount of computing resources. And so it's a good thing that by that time, you could get a gigaflop for 13 cents, right? And this allowed them to render the city of San Francisco with incredible detail. It took 4 render farms, 46,000 servers, and still took an average of 83 hours to render every single frame. So they're distributed between San Francisco and Los Angeles with, I think, 3 farms in LA and 1 in SF. And together, over a period of 2 years, they pumped out this beautiful movie, taking advantage of the leaps and bounds we've taken in CPU. And then in 2016, Deadpool came out. Who here saw Deadpool? Well, that amazing intro, that 2-minute long intro with all the crazy cars flying around and bullets and like the still shot with a city in the background, there were no real cameras involved in that. And in fact, there were no real actors involved in that, and there were no real props involved in that. Every single shot of that first 2-minute intro of Deadpool was entirely realized in a computer. There is no human here. There was never a human here, and there was never a camera to capture the human. Every pixel that you see in this image was entirely rendered in a computer. People used to complain that directors were using too much CGI, and they've kind of stopped complaining, but it's not because directors are using less CGI. It's because you just can't tell anymore. So in 2016, Pixar went path tracing only. They recognized that all the legacy rendering pipelines just didn't make sense anymore. Compute was cheap enough that you could go with the thing that gives you the best images. And so they just cut all the old code for RenderMan, their proprietary renderer. And they went with pure path tracing from that point on. And by 2016, you could get a gigaflop for 8 cents. So if you've seen any of these movies, then you've benefited from the algorithm that we're going to talk about today, from path tracing and Monte Carlo integration. And something that I think is super cool about this, check out the lower left frame. That never existed, right? There was no actress involved. They actually found it simpler to take a 3D digital scan of the actress and then just pose her in this scene and then render it, but you can't tell. And all of these things are predicated on statistical math that came about to make the atomic bomb. So all of these movies, every modern bit of 3D computer graphics that you see can trace its roots back to the nuclear bomb. So about a year and a half ago, someone linked me to Disney's Practical Guide to Path Tracing. And whoever it was owes me hundreds and hundreds of hours of my life back, because this topic really sucked me in. But it's a fantastic guide, and I'm going to crib a couple of their images to illustrate how path tracing works. Imagine a real scene. You're outdoors, there's the sun is shooting light, shooting photons onto all the different surfaces in the scene, and it's all bouncing around. It hits a tree, loses a little energy, hits a blade of grass, loses a little more energy, and eventually comes to your eye. There's uncountable levels of photons, uncountable numbers of paths in this scene. No computer could ever simulate it. But we want to simulate it, because eventually, if you're making a 3D film, some of those light rays are going to make it into a digital camera, a virtual camera. But it's going to be like 99.999999% wasted computation. If you're, all those red rays, they're completely useless. They never end up in a camera. They never influence the image at the end. Well, one of the cool properties of light rays is that they're bidirectional. It doesn't matter if a ray bounces from the left or bounces from the right. It loses the exact same amount of energy either way, as long as it's bouncing off of the same surface. And so the way a path tracer works is it actually shoots rays out of the camera. So you shoot light rays from the camera into the scene. They bounce around the scene, and eventually they hit something that's bright. Maybe it's the sun, maybe it's the ambient brightness of the sky, but eventually they'll hit something that's giving them light, and then you trace that path backwards to the camera, and it resolves into a pixel. And that's the basic idea behind path tracing. And it's actually so simple. If you check out the Wikipedia page for path tracing, you'll be amazed by the pseudocode that translates into this Go. Right? And this is actually working. You could run this. This is something that would give you a path traced image. And it's really, really basic. You basically have a trace function that takes an array and the number of bounces you want it to complete, and then it returns some level of brightness. So this would be a grayscale path tracer. If you exhaust your bounces, then you just say, all right, well, we never hit anything useful. And then you just intersect it with the scene. Maybe the scene's made up of triangles or cubes or whatever. It can be any surface. And if you hit a light, then you just return the light. OK, I found a light. We finally found a light. This path is done. But if you don't, then you bounce it in a completely random direction. Doesn't matter. And then you recursively trace that path until eventually one of these does hit a light. And at every single bounce, that light path loses a little bit of energy from the reflectance value of the material that it's bouncing off of. So something that's colored black might return a low reflectance close to 0, and something that's colored white might return a high reflectance close to 1. And it recursively loses energy until eventually it gets back to the camera and resolves into a pixel. So this is a working Go path tracer. And so when I read the Wikipedia article and watched Disney's introductory guide, I was like, well, I have to do this right now. I can't not build one of these if it's that easy. So I was in a cafe, I was hacking on some stuff. I was like, I'm going to spend the next couple of hours building a path tracer. And I did. And then my wife, who was my biggest supporter in all things, she came to the cafe. She's like, what are you working on? I was like, honey, oh, wow, this is so cool. I just implemented the same algorithm that Pixar uses, and I rendered my first scene. It's amazing. She was like, wow, that sounds great. Show me, let me see what you've done. So I turned my laptop around, and I'm like, bam! And ever the supporter, she was like, oh, that's beautiful, honey. It's a beautiful white circle. And I was like, white circle? That's not a white circle, right? There's a scene, and in the scene, I created a sphere. And I gave that sphere light. I said, you're made of light. And then in the scene, I added a camera, and I told the camera to send hundreds of thousands of rays out into space. And some of those rays, they hit nothing, and they returned black. And some of those rays, they hit the light, and they returned the light value. And then, yes, eventually it resolves into something that looks like a white circle. But you're looking at like a glowing sun here. And as much as she tried to pretend, she still wasn't all that enthusiastic, which just made me realize that I had to keep working on this and going down this rabbit hole until eventually I was determined I would make an image that really, took her breath away. So fast forward a year and a half. I ran into two obstacles that Disney's primer didn't prepare me for. The first obstacle was math. I don't have an academic background in math. I can't pronounce most of the symbols here. And as I got into this subject, I just started wading through hundreds and hundreds of pages of stuff like this. And I chose this one in particular because I thought it was particularly cheeky for this person to call it basic, right? Like, introductory, right? So obvious. The second problem I ran into was JavaScript, and here's my big confession, right? Like, for the years leading up to this, I was the Node.js platform owner at Heroku, where I work. So I was responsible for all of our Node.js apps. I was responsible for the Node runtime and the Node experience at Heroku. And so for many years, JavaScript had been the language that I used every day at work. It was the one that I was most comfortable in. And so when I started hacking on a path tracer, I started in JavaScript. And the problem with that was that this scene that has, 5 spheres, a floor, a couple of lights, and it's really low resolution, took 4 hours to render. So when you're already not sure that you're getting the math right, that 4-hour feedback loop before you even know if something's glitchy was not accelerating my learning process. So at this point, I was like, all right, it's time to learn Go. I'd already been thinking about it because a lot of Heroku is built on Go. We love Go at Heroku. We have a bunch of great Go engineers. And actually, we have a booth out here. You should go meet some of the actually experienced Go engineers out there who've been doing it a lot longer than I have. And also get some awesome socks, because we have the best socks. And Go is fast. I had good resources for it, and it's pretty quick to pick up. And so this project is why I even got into the language in the first place. Oh, and since real time isn't quite a thing in path tracing, I'm going to start my live demo now. So I don't melt my laptop. I've got this running on Heroku, and I'm going to scale a worker up. Oh, good, the internet's working. And then I'm going to open this. Okay, so I've got one little worker rendering one little scene. And it's going to be kind of slow with one worker, but all right, so let me mirror my displays. Actually, I'll just move this over, that'll be faster. All right, there we go. Okay, so now we have this nice little image that this path, I wanted to make this toy. In honor of like Toy Story, I wanted to render this cute little pink gopher. So the pink gopher is going to be rendered along with a few different toys. And it doesn't look super impressive right now, right? Like that's not great. You wouldn't watch a movie that looked like that. But actually, I will probably scale it up a little bit to 10, because path tracing is an embarrassingly parallel algorithm. And so I'm going to say Heroku scale worker equals 10. And just to kind of give you guys a sense of what I'm doing, I'm just basically saying, hey, work on this. And I actually want a bunch of workers to work on this at the same time. And then we can check on the results of this trace later at the end of the presentation, which is a much more realistic timescale for a live demo of path tracing. So, all right. So now let's talk about how you build a path tracer with Go in plain English with as little math as possible. And just like a dusting of physics. So in 20 minutes from now, you are going to know how to build a path tracer with Go. And then we'll check up on that render and see how it's going. Hopefully it's all working. So my first question to you is, what is light? It's a particle. It's a wave. It exists on some spectrum. It can be polarized, right? But for a computer graphics programmer, light really has three important properties. It has an origin, it moves in a direction, and it carries energy. And we usually represent that energy as red, green, blue triplets. And so that's how most graphics systems represent light. Origin, direction, energy. And in Go, you could represent that something like this. There's a lot of different ways you could do it, but really three different vectors, each one of which have three different fields. And that's how it works in PBR. Next question is, what happens when light hits a surface? And this was one of the coolest things to learn about while I was researching this project, because it turns out that materials, even though they look so different, they all behave in really similar ways. When light hits any surface, it only does one of two things. It either reflects or it refracts. Just one of those two things. Metals are really the simplest material because they only reflect. They never refract. And then nonmetals can pretty much do anything. But what's important to note here is that even though once it refracts, it might interact with the material inside of the surface, it might get scattered back out of the surface, or in the case of something like glass, it might keep moving through the surface in to a deeper level, or it might reflect off of it and never go inside the surface. There are really still only two things. It's reflecting, or it's refracting in and then mingling with the material itself. And so what's really cool is that these two cups are really similar. Light is not working differently for the transparent cup than it does for the opaque cup. Right? Light is moving into both of these. The only difference is how far a light ray can move inside of the material before the surface disrupts it and scatters it back out. If you had a 9-foot deep, cube of glass, you wouldn't be able to see light going clearly all the way through it, because eventually even glass does diffuse and scatter light. So the only difference between these two cups is how long does it take? How far into the material can light move? So for the purposes of modeling this, all incoming light is reflected, diffused, or transmitted. And that's how we can make a 3D renderer. How do we simulate these three things with Go? That's where you get into bidirectional reflectance distribution functions and bidirectional transmittance distribution functions. And when I first saw this, I was like, what? But it turns out that just like a lot of the academic research I was going through, this is a really complicated name for a really simple idea. It's a pure function that describes a material. Its inputs are the angle at which light is coming in and the angle at which light is going out. And it returns a number between 0 and 1 representing how much of that light is allowed to bounce out. So a number close to 0 will make a dark material. A number close to 1 will make a light material. This particular BRDF is very simple. It would give you something like chalk, but the most perfect chalk you'd ever seen. Right? It basically scatters light in all directions equally. And that's all it is. One key property of a BRDF is it has to be bidirectional, right? AB and BA have to return the same value because of the fact that we might be sending it from the camera, right? So, so it's light goes in, light goes out. One of the cool things about this is that the physics have all been done for us. So you don't actually have to figure out how to write a BRDF or a BTDF, because people have already written the microfacet BRDF, the OR and the AR BRDFs. These are all published by companies like Pixar and Disney, and actually Google just released an open source project called Filament that publishes all of its BRDFs. And so you can just go take what physicists and programmers have collaborated on and basically just copy paste it into your program. With Go, it requires just a hair of translation from whatever language it was written in, whether it's C++ or GL or whatever. But they're not very big, they're not very complicated, and they're mostly just math. So you just translate this math into Go, and then you have realistic, physically based BRDFs. So some of you who know more about statistics than I do might be thinking, but that's just one path. right? We hit a surface, and then we bounced in a random direction. And then we hit another surface, and bounced in another random direction, and so on. Won't that just lead to noise? Like, there's no system there. Aren't we just going to get noise from that? And that is exactly the right question to ask. And it's where Monte Carlo integration comes in. So this basic paper from before, once I wrapped my mind around all this, it actually became very simple. So I'm going to jump straight to the simple explanation of Monte Carlo integration that requires no math. First, you sample a bunch of values randomly. You add them all up and you average them. And that's probably close to the real answer. That's it. Like, that's the whole thing, right? That's Monte Carlo integration. So what it looks like in practice is this. This is something rendered with PBR, with this Go system. And initially, it does look like noise, right? You can see that it's not perfectly predicting all the paths here. This is after just a couple of seconds. You run it for another 30 seconds or so, and it starts to clean up a little bit and starts to converge on something closer to reality. You let it run for several minutes, and you get something that is fully converged, where there's going to be a little bit of error in each one of these pixels, but the error is so small that you basically can't tell. Right? So this is how path tracing and Monte Carlo integration work together to give us answers to questions that would otherwise be impossible to ask, like how do billions and billions and billions of photons bounce around this environment? So once you've built something like this, with some spheres and some cubes and some basic colors, right? Oh yeah. For the other JavaScript escapees like me, it was about 15 times faster than JS, right? Which is great, because that means something that'll render in half an hour in Go would take hours in JavaScript. So like this scene, I would just be like leaving my laptop on overnight, just checking in the morning. Not a great feedback loop. So how can we make more interesting images than just little spheres and reflective balls and cubes and stuff like that? This is where it starts to get kind of fun. Because you don't have to change the algorithm at all. You just have to give it new surfaces to bounce off of. So one of the things we can do is we can give it more complex geometry. Right? And all of these were rendered in Go, by the way. All of these are rendered with the PBR project that's MIT licensed and open source right now. So complex geometry like Legos. Man, my little clicker is really just going crazy on me. Complex geometry, you can see that you can do curves here. You can render things like the Millennium Falcon with really intricate surface detail. You can render things that have millions of triangles, each of which have different types of materials. But this changes nothing about the core algorithm. All it means is you need to write something to parse something like an object file that just says, here's a billion triangles and where they are in the world. And then you just run the exact same recursive algorithm on all of those triangles. The next thing you can do to make more interesting images is to use real materials. Like here's a happy Buddha rendered in gold. Here's a glass rendered in glass. And again, you can lean on existing physics, research that people have already done. You don't have to invent any of this stuff. People have measured how glass works and how standard like crown glass, how clear it is. And then you just kind of translate the existing physics into Go. So I didn't compute any of these numbers. I just looked them up from a table in some physics textbook. And here's my favorite little hack to make more interesting images. It's called image-based lighting. And the reason I like it best is because it was the simplest to implement. It's one of those things where you write the code for it, and you're like, there's no way in hell that is going to work. And then it works on the first try, and you never have to touch it again, right? So like this is a lion statue that's rendered in this environment, but also in this environment, and also in this environment. Right? And each one, it looks like it belongs to the environment because it's interacting with the light around it. And it is the simplest thing. Remember previously I said, if you never hit a light, you just return black? Well, all you do is, instead of returning black, you just like look up the color in the background, right? You have a background image, like in this case, it's this little like city scene in Italy or something. You just say, well, that light ray that would have returned black, what pixel would it hit if I let it go and hit the picture that's behind it? And you return that instead. And suddenly, it looks like it belongs in that setting, right? So, this was my first Go project. The first commit is hello world, right? And it evolved into this. So I have learned a lot about Go in the last year and a half as I've been working on it. And I still consider myself a little bit of like a Go, novice. One of the traps that you can fall into with Go is one that I've fallen into, where you learn just enough to do exactly what you want, and then you're just like, all right, well, that's good. So the guys back at the Heroku booth know a lot more than I do. But I wanted to call out a couple of light bulb moments that I have had over the course of this project, where either I encountered something that I hadn't read before, or I read something, maybe something really popular by like Rob Pike, and then I misinterpreted it, and it did something incorrectly, right, that led to a lot of confusion. And so there are kind of two little moments like that that I want to go over. The first starts with lines like this. Notice how many vector 3s there are. When you're writing a 3D rendering engine, it's just full of vector 3s, x, y, z values. And so here, I've got two angles, the incoming angle and the outgoing angle. And they're directions, really. They're directions of movement of light rays, and they're both vector 3s. Then I have a Boolean that basically says, does this material absorb or not? And then I have two other vector 3s, and to this day, I'm actually not quite sure what they are. I can't really remember. And what this started to lead to, because vector 3s, can make operations, like have operations with other vector 3s, is that I started telling Go to do things like this. Right? Direction is 2 meters up plus a halogen light bulb. It doesn't make any sense, but of course, the system would do it because they're all vector 3s after all. And it started getting really easy to introduce these quirky bugs. I'd be like, position of this is fuchsia turned by 90 degrees. Because all of those things are represented by vector 3s. And I started getting very, very strange bugs that were super hard to track down. And eventually, I found out about this feature of Go that I initially thought was going to be useless. And it's just a type define, or a renamed type. And this, to you expert Go programmers, is probably old news, but to me, this was revelatory. This changed the whole architecture of PBR, because suddenly, I could say, OK, well, a unit vector is a type of a vector, and a vector is a type of a vector, and they have some operations that they can do across those bounds, but most of the time, you can't combine them. Right? Most of the time, you have to go from one to the other and back on very tightly controlled boundaries. And what was neat is once I did this, once I started using type defines and I started using directions for directions and energies for energies and so on, I found all sorts of bugs, places where I was doing operations on things, assuming they were unit vectors when they really weren't, or they weren't necessarily. And it was just fantastic. So suddenly, the compiler was helping me find all of these hard to track down issues. And, weirdly enough, performance improved. Because there were a bunch of other places where I was like, oh shit, have I already converted this into a unit vector? I don't know, so I'm just going to do that here. And so I was doing it more than I needed to. I was doing it preventatively. And once I was guaranteed to never do a unit vector operation on a non-unit vector, I could just delete all of those sort of paranoid function calls that I was making. And it actually sped up the program and made it safer. I did this for energies as well, because energy, RGB, XYZ, it's the same thing. But you can't gamma correct a direction. You can only gamma correct a color, right? So with energy, it's also a vector 3, but now it's also its got its own boundaries where it only shares certain operations with vector 3s. And it sounds so simple, but it really changed how much frustration I was experiencing developing this program. The next thing is actually a quote from, and then it ends up looking like this, right? It's much easier to understand that these two are directions, that's a location, and that's an RGB value. And even if I forget what they are, if I accidentally try to do an operation on one with another, it won't let me. Like, Go simply won't let me. So that's beautiful. So years ago, at Heroku's Waza conference, Rob Pike said, parallelization can fall out from concurrent design. I think that's a really elegant statement. He also said, Go routines aren't free, but they're very cheap. And as a new Go developer, I obviously watched and read the concurrency isn't parallelism thing. That's where these quotes are from. I was like, that's interesting. That's really interesting. And it directed the architecture of PBR version 1. And I was like, all right, so this is mostly just a bunch of pure functions. They're just reading data and then giving values. Like all the paths, that's just like a pure function. The only time I ever need state, and the only time I ever need to write any kind of state, is when I'm recording the result of a path and like adding it up somewhere in basically like an image buffer. So the beautiful concurrent design of PBR would be to have one part of the program that is solely responsible for writing and for changing state. And then to just have a whole bunch of Go routines, like hundreds of thousands of Go routines, just tracing paths and then returning whatever the value of that path was to this thing that writes state. That's very elegant. And it does work. It's just really, really slow. And what I found was that safe concurrency doesn't necessarily lead to performant parallelism. And what I kept doing is increasing the number of pixels, or the number of paths that a Go routine would trace, and then like have a big buffer of them and then send it back to sort of the parent. And every time I made that buffer bigger, the program ran faster. And eventually I was like, OK, maybe I don't even need to do all this stuff. Maybe I just need to have each Go routine work completely independently and just trace the whole image and then just send that buffer back to the thing, and then it just like merges that image on top of the existing image, right? So every Go routine now has its own little local copy of what it's tracing, and then once it sends it back, it just forgets about it and then starts a new image. And that turns out to be much, 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 much faster because I was misunderstanding, exactly how parallelization will fall out of concurrent design. Because even though it can fall out, it might not run fast, and even though Go routines are cheap, communicating between them is pretty expensive, especially if you're doing it in the terms of like billions or trillions of paths, right? So that's something that kind of bit me as a developer because I was doing what I thought was exactly what you were supposed to do, and my program was really slow, and it took a while for me to figure this out. So now you are all ready to write rendering engines. You know everything that you need to know. You know about as much as I do. And this is a great time to get into this because 2018 is like the year of ray tracing. This is a real-time ray traced game demo that came out earlier. This was just released by NVIDIA at SIGGRAPH a few weeks ago. Every major player, from Microsoft to AMD to NVIDIA, is kind of getting into ray tracing. And it's actually because of that sort of Moore's Law thing that I was showing at the very beginning of the presentation. It's gotten so cheap to have huge compute power that commodity hardware can do it now. You don't need a render farm necessarily to render these really amazing images. So there's all this research out there that hasn't been implemented yet. We have an embarrassingly parallel algorithm, and it's really, really fun to mess around with. So this is just a great field for, for gophers, I think, because the other thing that Go gives you when you're getting into this is that you don't have to learn like advanced C++, and you don't have to learn how to program GPUs. I think everyone here is capable of both of those things, but doing one of those while you're also learning about all this rendering stuff is a really tall order. It's a high barrier to cross. So for me, it was lovely to be able to work within this great concurrent garbage collected ecosystem while I'm figuring out all this math and all this physics. And I would love your help, right? So go online, go to PBR. If you are even a little bit interested in this, I would love pull requests. I would love issues. It's really easy to get started. Every image in this presentation has been rendered with PBR, and it's easy to get started. You just go get it, and you can make any of the samples, make Lamborghini, make shapes, make whatever, and it will render it locally, and then you can kind of play with it. And it's a really fun thing to play with. Oh, and also, I'm trying to render this. Hopefully, my workers have actually been running. Let's see. All right. Yeah, so we scaled it to 10. So now I'm going to refresh this page. Let's see how far they've gone. Oh, yeah. Come on, that is not a bad likeness of this little guy, girl, whatever. So thank you, everybody, for participating. And I'll be at the Heroku booth if you want to talk afterwards.